All right, hello and welcome to Unit 3. As we move into Unit 3, we're going to start talking about our first unit that doesn't deal with the living world. Units 1 and 2 were some more big picture things. Unit 3 deals specifically, as you can tell by the title, with populations. We're going to split Unit 3 into two parts. Part 1 is going to deal with non-humans, basically, and just generic population factors and things that we're going to look at. And then part 2 will deal specifically with the human population. First thing we're going to talk about is specialist and generalist species and the differences between them. The dichotomy here has some specific characteristics that make it fairly easy to try to pigeonhole an organism into one or the other. There is a bit of a spectrum here, and we'll talk about that as well with R and K selected species. As the name suggests, generalists have a larger range of tolerance and a broader niche in their ecosystem. Specialists do not. They have a smaller range, typically more prone to extinction given if something happens to one of the things that they require, whether it's food or habitat. Usually, specialist species have a weaker ability to adapt to new conditions. Generalists are much more adaptable. So if we're talking about an organism that can eat lots of different food sources, or can live in a larger range of temperatures, let's say, we would classify that as a generalist. Specialist would be something that only eats maybe one very specific kind of food, or has a very, very narrow range for something maybe like temperature, or if we're talking about pH as an example for marine organisms. You can see on this slide how we would compare and contrast generalist versus specialist, talking about the niche being narrow and versus broad, the adaptability we mentioned, as well as the likelihood of going extinct, a specific set of resources versus a variety of resources, namely for foods, high ranges of tolerance, high versus low. And then the last one here goes back to, we talked about disturbances. Generalists will do well with conditions that might change or fluctuate, whereas a specialist require constant conditions within their environment. Moving on to that, another population characteristic we'll look at is what's called R versus K selected species. This has to do with the birth and development of organisms from a specific species. One way to think about this is quality versus quantity. So a K-selected species is the quality, in quotes there, meaning that we have very few offspring, but the likelihood of those organisms surviving and making it to reproductive maturity and then having offspring of their own is very, very high. The R-selected species have lots of offspring, and the likelihood of them reaching reproductive maturity and reproducing successfully is much lower, given that you have so many offspring. So we have two different reproductive strategies here. One is very few organisms, but everything involved is essentially there to ensure that the organisms survive long enough to reproduce. Whereas with the R-selected species, there isn't anything in place. It's just have as many offspring as possible, and that's your best outcome as far as reproductive survivability. Lots of offspring. We expect very few of them to make it to grow and develop and reproduce themselves. A couple of other things here. Few reproductive events, very heavy parental care with the K-selected species. and a long lifespan, as well as a longer time to sexual maturity. And that reduces biotic potential, meaning that those organisms don't have as many offspring. But because they're involved in the care and upbringing, so this is where we would see organisms, a lot of mammals, birds that tend to care for their young until they're old enough to be on their own, would qualify as K-selected. Organisms that we can typically think of as R-selected are ones that would just have a lot of offspring, as many as physically possible. Insects and plants are a very good example. A note here is that when we talk about invasive species, which we'll get into more detail with in our last unit in Unit 9, but invasive species, one that moves into an area and is successful, is more likely to have two specific things that we've talked about, or fall into two of these categories that we just mentioned today so far. Invasive species are more likely to be R-selected as far as their reproductive strategy, and they're more likely to be generalists as far as what kind of conditions they can tolerate. This chart should be available if it's not in your textbook, a similar version of it for comparing and contrasting K and R. One thing we will say, though, as far as reality, is that while we have two different delineations here about an R-selected or K-selected, every organism and species are different. So the reproductive strategies here do fall along a spectrum. We might think of something as being more R or more K, but when we're talking about test questions, it should be fairly obvious what the organism is meant to fall into if we're denoting an R and a K species. Usually there's some kind of clues given there as far as what kinds of varieties of food and how many offspring are had and how much parental care is involved, things like that. One other note talking about disturbances as well as invasiveness, K-selected species are the ones that are usually going to outcompete the R-selected species, if they're invasive, will outcompete native K-selective species because of the fact that they can reproduce rapidly and grow rapidly and do well in that environment. K-selected species are also going to be more likely to go extinct if they cannot adapt to those changing conditions. Now, we don't want to completely group K-selected and specialist together because that's not true. We have a lot of specialist insects and specialist plants, which would still be R-selected. There are just organisms that might be generalist R-selected species that can do better in a specific environment than a generalist K-selected species. All right, the next one is survivorship curves. And you can see here we have three general categories for a survivorship curve. And this gives us an idea of, for a specific organism or for a specific species, how many individuals are going to survive over the average lifespan. What this information is going to give us is relative survival rates of a group of individuals. Now, with our type 1 and type 3, those are going to be the easiest ones to kind of look at. Type 1 and type 3 are going to respectively fall into what we just talked about with a categorical K-selected species for a type 1 and a categorical R-selected species for a type 3. The slower the drop in the line, the longer the average lifespan, which is why we see the type 1 curve in the blue line up at the top. Those organisms, however many, basically being born, ensures a very likely chance that those organisms will grow and survive for basically what would be considered a regular lifespan. The type 3 curve having the large drop-off looks like an R-selected species because being born, most of those organisms are going to die very early on in life, and then the organisms that do survive are a much lower number. Now, with type 2 is going to be somewhere in between R and K, and the easiest way to think of it is just a steadily decreasing survivorship throughout life, meaning that not all organisms are guaranteed to make it through their full lifespan, but the longer you're alive, the more organisms from that population are going to start dying off, and we start to see scattered uh, lifespans as far as age for those organisms that are in type 2. The type 1 and type 3 falling into K and R selected information is all explained right there, basically going right in line with everything we said from our R and K selected species stuff. The next population piece here is carrying capacity. Carrying capacity we denote with a capital K in environmental science. And this is probably something that you have a little bit of maybe some background or experience with already, but we're going to talk about it in a little bit more the real sense here. Now, we've talked about populations, and this is probably something that might have come up in previous classes for you, but species reach a carrying capacity, meaning the maximum number of individuals that can be supported. So you have limited resources in that environment, and those resources within that habitat and that environment will basically say this is how many organisms can survive here. Basically figure 1, that left graph there. That's the theoretical one, but it's usually the simplified one that we look at, where a population will have early growth be exponential and grow rapidly. The growth begins to slow, and then that growth eventually falls to 0, meaning the population growth is not changing, and the same number of organisms will more or less be found in that population. A more realistic view, and we'll see this in one of the activities we should get to in this unit, is the idea of overshoots and die-offs, where a population grows exponentially and will actually overshoot its carrying capacity. When it does that, there's not enough resources to support all of the organisms up here, and then a die-off happens, where more organisms than normal would die due to the lack of resources. Then, as those organisms die and resources become more available, we get another overshoot and then another die-off subsequent to that. And we basically just get this fluctuation back and forth around the carrying capacity line, because in reality, you're not going to have the exact same number of organisms in a population being born as the ones that are dying. You're always going to have some fluctuation. Those overshoots and die-offs are explained in a little bit more detail here. We will do a lab involving lynx and snowshoe hare numbers to simulate this data. Speaking of, this graph looks very much like what we'll see when we do our lab involving lynx populations and snowshoe hare populations, where we're going to see these overshoots and die-offs happen due to the predator-prey relationship. The hare population would grow because there are few predators, being the purple line there. And as that population starts to grow, the lynx population itself will also start to grow. And that means because they have more food, their populations are going to grow as well. As they eat more of the hares and the hares start to die off, the lynx population will hit a limit, and that will also lead to a die-off of those organisms. And we will see this cycle basically fluctuate up and down until it stabilizes. Now, speaking of resource availability and how it affects population growth, that's the last topic for our non-human population topics here. The key piece being that population growth is limited by a number of factors. Some are just based on what resources are available, and some are based on how many organisms are actually there within a population. So a couple of things we use just very quickly to look at population characteristics. The number of individuals, the population density, how many individuals are in an area, and then distribution, how individuals are spaced out compared to one another. Distribution we typically look at as being random, where we would find them in a population. Uniformly distributed, spaced out for enough available space, or clumped together throughout the habitat. Other factors we look at, the last one that just deals with individual organisms is sex ratio, which is usually more closer to 50-50, but things that we've already talked about like die-offs and bottlenecks can skew the sex ratio, and that would have an impact on population growth. If a bottleneck or a die-off happens to affect too many organisms, specifically females for most populations, that's going to limit population growth and slow it. We also look at factors that are based on how many organisms are there, and we call these density dependent or density independent factors. And these are really easy to differentiate. A density dependent factor has to do with a resource, some resource that is in that ecosystem. Food, habitat, available water, if we're talking about marine organisms like, say, algae, light, disease. All of these things limit population growth based on their size, meaning that if you have a small population and a specific amount of whatever that resource is, it won't have much of an impact. But as the population grows larger, it will have a much greater impact on that population. So with a small population, food is not a concern. As the population gets larger, food becomes a concern and organisms begin competing for it. That's going to limit growth. Density independent factors do not take into account population size. Natural disasters are really the only thing we'll talk about here. So hurricanes, which we just saw a couple examples of here in the US, tornadoes, fires, floods, it doesn't matter the population size. Those types of events, it doesn't matter if there's 100 individuals or 100,000 individuals. If a flood happens in a habitat, it's going to take out whichever organisms are there. Now, as we talk about population growth, we come across something that's called biotic potential. You'll see this in a few different areas. Biotic potential is basically growth rate. If you have no limiting resources, we call this the rate of natural increase. How fast, how much growth can actually happen within a population. Now, at the early parts of population growth, this can happen for most populations because you have a small population, small numbers, very few limited resources. So populations can grow exponentially without any kind of limits. As the population continues to grow, that competition for resources, for those shared resources, the space, the water, the food, it's going to limit how fast those populations can now grow. They're not going to be growing any faster. They just might be growing a little bit slower until they eventually reach that carrying capacity point. One of the ways that we measure this is by just simple addition and subtraction. As simple as this might sound, this is a piece of math that we need to know for our test. There are inputs, immigration and birth, so organisms migrating into an ecosystem plus the individuals born. And we subtract, this is a typo here, this should say emigrants or emigrations plus deaths. So emigration with an E, take organisms that migrate out of an area, and deaths, those are going to decrease population size. There's a few more pieces of math that we'll get into with population growth as far as percentages and things like that when we get to the second part of our Unit 3 talking about human population growth in more detail. But that's it for the first part of our Unit 3 notes review.